Okay, so we're ready to tackle the last topic of this chapter, which is, well, that's not true. It's not the last topic of this chapter. It's the last main idea of talking about DC circuits, and that's the idea of finding the current in sort of more complicated multi-loop circuits. And before we do that, we need to talk about a little bit more about energy in an electrical circuit in general. If we've got oops, let me just really quickly just make up an electrical circuit here. Suppose we've got a battery and a resistor and another resistor. And let's say this has a voltage of 9 volts, and this has a resistance of let's see, 2 ohms, and this has a resistance of 1 ohm. It's easy enough to calculate the current flowing through the circuit, right? If we just use Ohm's law of V equals IR. The total resistance of the circuit we can see pretty easily. It's 2 resistors in series, so the total resistance is 3 ohms. So the current through this simple one-loop circuit is equal to V over R, which is 9 volts over 3 ohms, or 3 amps of current. If we ask for the individual resistors, what's happening as the current flows through this resistor back to the negative terminal of the battery? Remember, what a battery is a source of EMF, or a source of electrical potential energy. And from the positive to the negative terminal of the battery, you can almost think of it as like a ball rolling downhill. It starts with potential energy at this terminal. It goes through the circuit. When it gets back to the negative terminal, we assume that all of its energy has been expended. It's at the bottom of the hill, as it were. And then the battery sort of lifts it back up again to positive electrical potential energy. Because in an electrical circuit we neglect or we ignore the resistance of the wires, the only place where this electron loses energy in a circuit is in passing through the resistors. So the change in voltage, or what we sometimes call the voltage drop, over each resistor is equal to IR. So each charge loses an amount of electrical potential energy per unit charge given by I times R. So across this resistor, there's a voltage drop of 2 ohms times 3 amps, or 6. Sorry, I said one thing and wrote the other. Let me write that again. There's a potential drop across this resistor of delta V equals IR. I don't know why I can't. There's enough room for me to write in here. Delta V equals IR, which is 3 amps times 2 ohms, or 6 volts. Across this resistor, there's a voltage drop equal to IR of 1 ohm times 3 amps, or 3 volts. And what we can see is that the sum of these voltage drops, 6 volts over this resistor and 3 volts across that resistor, is equal to 9 volts, the total potential difference between the positive and negative terminals of the battery. So as you cross over each resistor, there's a change in potential energy per unit charge given by IR, where I is the current through that part of the circuit, and R is the resistance of that. And if you add up all those potential drops around the circuit, you get the total potential difference between the terminals of that battery, or the plugs of that wire, if you're talking about household wiring. Whatever that potential difference is, we assume that the charge loses all that electrical potential in traveling from the positive to the negative side, and then is pushed back around the circuit, or the next batch of electrons is pushed around the circuit again. So this idea of a voltage drop is relevant to, say, for example, if you are measuring the voltage in a circuit. And we're not going to get much chance to do this for real Maybe I erased too much of that, huh? We're not going to get much of a chance to do that for real this semester, but we are going to do a simulation lab where we do that. If we had a voltmeter that measures electrical potential difference, and we connected it to the circuit between various points, we would get different readings depending on where we connected those wires. For example, if we connected a voltmeter, let's use red for the wires of the voltmeter. If we connected the voltmeter I don't know why. Oh, for some reason I know you can't see this, but on my screen this should be showing up as a little pen, and it's not. Okay, if we connected the voltmeter here and here, what we would measure is the potential differences between those 2 points in the circuit, which has got a battery in between them. So their voltmeter would read 9 volts, which is the potential. Which is the potential difference of that battery. Somehow I didn't close that line. 9 volts. If we, on the other hand, connected the battery to either side of this resistor, okay, say from here, 1 lead of the voltmeter here and 1 lead of the voltmeter there, what we would measure is the potential difference between the circuit on this side of the resistor and the circuit on this side of the resistor, which experiences a potential drop of 6 volts. So we would read 6 volts, a potential difference between those 2 points in the circuit. Likewise, if we connected the voltmeter to this point on one side of this resistor and this point on the other side of that resistor, it would read 3 volts, the potential difference or the potential drop across this resistor. If we, by the way, connected a voltmeter to a circuit, say here and here, that would read 0. There is no potential difference between 2 points on the same wire if there's no battery or resistor or anything between them. Again, we're ignoring the fact that the wire itself has some resistance. So 2 points on the same wire with nothing in between them are at the same electrical potential. This is all a tool then in describing circuits with a more complex configuration. I'm actually going to skip ahead a little bit. Imagine we had a circuit that looked like this. This is example 26.9 in your book. We've got, and I'm kind of stunned that it starts with such a complicated example, but there you have it. We've got a circuit with 1, 2, 3, 4, 5 resistors. We've got a circuit with an 80-volt battery and a 45-volt battery. And we need to figure out, or we're asked to figure out, what is the current through these various branches of the circuit. We can't really do that by just adding up resistors in series and parallel because of this presence of a battery in one of the branches of this battery here in this branch of the circuit, but not in this branch of the circuit. We can't just add these together because these 2 batteries will affect the different branches of the circuit differently. So this is actually a much more complicated question than we can answer just by adding together resistances and using V equals IR. We have to analyze the circuit in terms of the potential difference around a loop. If you start at one place in the circuit and go around a loop and come back again, you're guaranteed of a couple of things, and those things you're guaranteed of are called Kirchhoff's rules. Your book summarizes them in chapter 26 this way. First, there's what's called the Junction Rule, which is if you pick any junction point in a circuit, any place where the current splits or comes together, the sum of all the currents entering that junction must equal the sum of the currents leaving that junction. So conservation of electrical charge says that whatever current comes into a point in a circuit, that same amount of current has to go out. The second of Kirchhoff's rules is called the loop rule, which says if you go around a whole loop in a circuit, the total change in electrical potential has to be 0. Wherever you start, if you come back to the same point again, you're back at the same potential energy. And hopefully it's obvious why that's the case. Just like if a pendulum swings from one point and swings back to the same point again, its gravitational potential is the same. So what we want to look at is how do we apply this to an electrical circuit. So let's take a look at this diagram in your book from example 26-9. The first thing they do is they label the current in the different branches of the circuit. And this is something that, just like when you set up a kinematics problem, you get to choose the direction of positive and negative. You can choose to call the positive y direction up and the direction of gravity is negative, or if you're talking about something falling from a tall height and you know it's going to be moving down, you can call down negative and make G, sorry, you can call down positive and make G positive. You get to choose the directions here. So when they choose a direction for this current, you sort of try to guess which way you think the current's going to go. So here's a battery, here's positive and negative, so you expect the current to kind of go this way out of the battery and then come around this way. Here's a battery, positive, negative, current goes from positive to negative, so you kind of expect the current to go around like that. So the directions that they've drawn these currents 1, 2, and 3 in the diagram sort of correspond to that guess of which direction the current is going. If you guess wrong, and sometimes in a circuit where there's two batteries kind of pushing in opposite directions, it's not always clear which direction the current's going to go in each branch. If you guess wrong about the direction of the current, you'll just get a negative sign at the end, just like if you guess wrong about the direction of the positive and negatives in a kinematics problem, you just get a negative sign, and it means your velocity is in the opposite direction. So in this particular situation, they've got this current I1 going around this way and I2 going around this way. The other thing is that you have to look at the setup of the circuit and figure out what your branches are. So you've got this outer loop and you've got this inner part of the circuit here. And if you just pick a place in the circuit and say, I'm going to start here, say I decided to start here at point C, and I go from the positive terminal of the battery through the circuit, and I reach here and my current splits. Every time the current splits, you need to label those currents. So I've got one current here before the split and then two currents after the split, and then they come around and they come back together again. So you've got this other junction point D. So at the split, we know that I3 going into that split has to be equal to I1 plus I2. The amount of current going into that junction at point A is equal to the amount of current flowing out of that junction. That's Kirchhoff's junction rule. So every time the current splits, you get an equation that that gives you the relationship between those charges. By the way, there's another way to do this, and this isn't the way I learned it. In the past, I have showed it to students the way I learned it also, and I think that's a huge mistake because I think this way is actually easier, even though it's not the way I learned it. So this junction rule gives you an equation with three unknowns, I3, I1, I2. We can't solve an equation with three unknowns. If you've got three unknowns, then you're going to need three equations. So you might guess that we need two more equations if we're going to solve this problem. Where do those other two equations come from? Those other two equations come from each of these loops. And you consider each of these loops independently. You can start anywhere you want in the circuit. And you can choose your loops to be anything you want, just so long as you cover all of the circuit. So suppose I wanted to start here at G and do a loop all the way around the outside like that. Okay? That gives me all this part of the circuit, but it doesn't get the middle. I would have to choose another loop, let's say start at B, that goes around maybe like this. And now I've gotten the whole circuit. I've colored in all the parts of the circuit. You don't have to choose those two loops. You could choose one loop that starts at B and goes around this way and gets back to B, and another loop that starts at H and goes around this way and gets back to H. It doesn't matter where you start your loops. It doesn't matter which direction you go around in your loops. All that matters is you get your signs right when you go across the batteries, and that you keep track of your currents, and that you make it all the way around the loop. I don't know, should I check your book and see where they start, or should I just start where I want to start? I'm not gonna check the book. I'm gonna start at D, and I'm gonna go around a loop like this. Okay? In the direction of current 3 and the direction of current 1, around like that. And I'm going to count up all the changes in potential that I encounter while traveling around my loop. Okay? So I start at D, I go this way. The first thing I encounter is a positive change in potential of 45 volts, plus 45 volts. I'm going from the negative terminal of the battery to the positive terminal of the battery. I'm increasing my electrical potential by 45 volts. The next thing I encounter is a resistor. And we just talked about the fact when you cross a resistor, your potential drops. It's like experiencing friction, right? So the change in potential that I experience here is minus the current, which in this part of the loop is I3 times R, which is 1 ohm. Then I encounter another potential drop across this 40 ohm resistor. Okay? So another negative I3 times that potential difference, that resistance is 40 ohms. Oh no, I've run out of screen that I can draw on. Can I scroll this over? 40 ohms. The next thing I encounter, if I'm going around the loop this way, is a potential drop across the 30 ohm resistor. Notice now I'm in the part of the circuit that I've labeled I1. My current has split here at junction A. So my current is no longer I3, it's I1. I'm in this part of the circuit. So my potential drop across this resistor is I1 times 30 ohms. So I experience a potential drop of minus I1 times 30 ohms. And then I go around my circuit and I'm back at D again. Because I'm back at the same point in the circuit, my total potential difference, my total change in potential has got to be 0. So when you go around your loop and you make it back to where you came from, all of these changes of potential, the positive change due to going up the battery and the negative changes due to going down the resistors, all have to add to 0. Okay? Now I do the same thing with a different loop. I can start at D again, but let's start someplace different, just to show that it doesn't matter. And then we'll go see what your book did, and hopefully your book made different choices than we do, and we get the same answer. So let's start at G. And let's take a loop that starts at G and goes in the direction of I2 and I3 around like this. And makes it back to G again. Okay? So if I start at G, the first thing I encounter, and let me use a different color for this. The first thing I encounter is I go up a positive potential difference from the negative potential terminal of the battery to the positive terminal of the battery, and that battery's got an EMF of 80 volts. So the first thing I encounter is a plus 80 volt increase in my electrical potential. Then I go down a resistor, okay, downhill, losing energy to electrical resistance. Notice this part of the loop I've labeled with the current I2, so that is going to be a potential drop of minus I2 times 1 ohm. Then I go, I'm still in I2, I'm still in this part of the loop, then I go across a 20 ohm resistor here, and that's going to lead to a potential difference of minus I2 times 20 ohms. Then I reach this point where my current, splits. I'm going on this part of the loop here. So I go across another battery. It's actually the same battery that I went through in my first loop. I'm going from negative to positive, so I'm going quote-unquote uphill. So that's going to be a positive 45 volts. My electrical potential is increasing. Then I go through this 1 ohm resistor. Notice my current here is I3, so that's going to be a potential drop of negative I3 times, what was that, 1 ohm? Can't see my whole thing. Yeah, times 1 ohm. 1 ohm. Then I go through this 40 ohm resistor. I'm still in the I3 part of the circuit, so that's going to be a potential drop of, that's a multiplication sign, minus I3 times 40 ohms. Then I get to A. Our currents are back together. I'm in the I2 part of the circuit, and there's no more resistors before I get back to G. So now I'm back to where I started, and I know that that total change in potential is 0. Now what have I got? Now I have got 3 equations, 1, 2, 3, with 3 unknowns, I1, I2, and I3. And I should be able to solve those. That's not particularly pleasant, solving a system of 3 equations with 3 unknowns, but we can certainly do it. I'm going to do something here that I do a lot, and it's bad form. It's bad physics, but it's good math. I'm going to throw all the units away. I don't like those omegas clogging up my my calculation here. I know my answer for the current is going to come out to be amps, so I'm going to rewrite these as just algebraic equations. I1 plus I2 is I3. That's the first equation. The second equation is 40, well, yeah, I'll leave it here. 45 minus I3 minus 40 I3 minus 30 I1 is 0. And then the next equation is 80 minus I2 minus 20 I2 plus 45 minus I3 minus 40 I3 equals 0. So those are my 3 equations. Obviously there are some terms I can group in those equations. So let's do that. I should probably switch to paper here because I know my handwriting gets hard to read on this tablet. So my first equation is I1 plus I2 is I3. My second equation becomes, let's move all the currents to one side and the potential to the other. So this gives me 41 I3 plus 30 I1 equals 45. If I did that right and didn't screw up a sign, you add these together, right? They're still going to have negative signs. You put them over there, and I just changed which side everything's on. I'm going to do the same thing with the next equation. Again, hoping I don't make a sign mistake. And sign mistakes are really easy to make in these problems, and that's one of the reasons I hate doing them. So we've still got 41 I3 plus 21 I2 equals 80 and 45 is 125. Okay. So hopefully this is beginning to look a little more pleasant. Here's a system of 3 equations in 3 unknowns. I1, I2, and I3, and I just need to decide what's the best way to solve them. Let's see. Let's eliminate, well, I don't know. What do I want to solve for? I guess the obvious thing to solve for is I3 here because it appears in both the bottom two equations. So let's take this and solve it for I1 and plug it in there. Okay? So if we solve that top equation for I1, we get I1 equals I3 minus I2. So the second equation becomes 41 I3 plus 30 I1, where I1, I'll do it all in one step, is I3 minus I2 equals 45. And the second equation, well, we'll do one more step and then we'll write the second equation. So that's 41 I3 plus 30 I3, that's 71 I3 minus 30 I2 equals 45. And then we'll go ahead and we'll write the second equation below that. 41 I3 plus 21 I2 equals 125. So how are we going to solve this? We could solve one of these for I3 or I2 and plug it into the other. The thing that I see right away is that if you look at the second terms here, they're both multiples of 3. So what I'm going to do is I'm going to divide the top equation by 10. And I'm going to divide the bottom equation by 7. Okay? And what does that give me? That gives me 7.1 I3 minus 3 I2 equals 4.5. Dividing the bottom equation by 7, I'm going to need a calculator for that. 41 divided by 7 is 5.857. We'll round that off to 5.86. 5.86 I3 plus 21 divided by 7 is 3. That's why I did this. Plus 3 I2 equals 125 divided by 7 is 17.86, more or less. And then I'm just going to add these two together and the I2s will cancel. So I've got 7.1 plus 5.86. Oops. That's 12.96 I3 equals 4.5 plus 17.86 equals 22.36. Which means that our current I3 is 22.36 divided by 12.96, which is 1.725 amps. And if we go to the book and look at their solution, okay, oops, hold on a minute. The solution in the book actually finds I1 first, but if we look at their solution where they find I3, we've got 1.7 amps, which is exactly what we just found. Now we've only solved part of the problem, right? In order to solve the whole problem, we need to take this 1.725 amps, plug it back into, say, let's go back to maybe this formula and find I2, and then go all the way back to this formula and find I1. I'll leave it to you guys to go through that algebra. I shouldn't need to show you guys how to solve a system of simultaneous equations. Having found I3 though, it should be fairly easy to go back and find I2 and I1 from the other two equations. If I really quickly, I'm going to go off screen to some place that you can't see. If you look at the example in your book does a loop that starts at point A and goes around the top loop and then around the bottom loop. It would be interesting, and maybe I'll do this just as a supplement for you guys. It would be interesting to go to to do the same problem over again, but do completely different loops. In other words, to do a loop that goes around the whole outside of the circuit, and then a loop that goes in the opposite direction around the inside of the circuit. The reason for doing that is to show that if you apply Kirchhoff's rules carefully, you should always get the same answer, no matter what loops you choose, no matter how you label your currents, no matter what the direction of your arrows is. So I might do that. I hate to do it because it's boring and tedious, and we already did this problem once. What I'll do is I'll encourage you to do that yourself as practice. Do the same problem again, the example in the book. And well, let me go back to the drawing. Okay. So what did we do? Let's remind ourselves what we did. We started at gosh, I don't even remember where we started. It was so long ago. We started at D, I think, and went around the loop this way, and then we started at G and went around the loop this way. Try doing this whole problem again, but instead start at H and go around the whole outside loop like this. Then start at B and go through, I don't care which, either way is fine. Start at B and go around this loop like this. Or, to really screw yourself up, start at B and go the wrong way around the loop where I1 and I2 are pointing at you, and you'll have to put a negative sign in front of all your currents. If you can do that and get the right answer, that's something, because like I said, it's really easy to make a sign mistake in these problems. I'm kind of disappointed that your book actually starts with an example as complicated as this one, because I would have done it with just one battery and 2 loops instead of 2 batteries and 2 loops and resistors in the middle loop as well. But once you can apply Kirchhoff's rules, there's no limit to how complicated a circuit you can analyze, and some of the homework problems for chapter 26 are pretty complicated and ugly. So I haven't decided exactly what I'm going to do after this video. Like I said, I might do a video where I do the same problem again with different loops, just to show that you get the same answer. I might do a problem where we do a simpler example that's not quite so complicated, that doesn't have quite so many batteries, but one where you get the directions of the currents wrong, because it's instructive to see what happens if you guess wrong on the directions of the current and it comes out wrong. Like I said, they're tedious, but we gotta do them. So I'll probably assign 1 or 2 of these for homework. I won't put one of these on the final, because, like I said, they're mostly just like the conservation of energy and momentum problems that I mentioned. They're mostly a proving ground to see if you can make it from the beginning to the end without making a sign mistake. And you guys know that I don't find those kinds of problems particularly interesting or instructive. But we got to do a couple of them. So I'll go ahead and stop it there. That's just over almost at 35 minutes for this video, which is longer than I like to go. Like I said, I might do a couple more practice problems just to show you the different ways you can do this, and to prove to you that it doesn't matter what directions you go in your loops and what directions you choose your currents, you will still always get the right answer.